Hi, good morning, everybody. Happy Monday. So, I'm not sure what's going on with WebEx these days, but it looks like now I hit the record button. It doesn't actually save to my desktop. It records it up onto WebEx's sort of cloud area. So, in order to watch this video, I guess I'll have to probably make this announcement on Canvas. You have to go to WebEx on Canvas and watch the recordings there, I suppose. Yeah, I don't know what happened. WebEx is a really weird program, so yeah, but I'll definitely remind you guys. I'll let you guys know on Discord for that. Um, so anyway, that's probably better actually because YouTube is not supposed to be used anyway. So at least this way now it's not through YouTube, so that way it's more official anyway. So um, two announcements. Okay, the first one, yeah. So homework 4 is due on Friday. Yeah, I'm sure YouTube was probably more convenient, but I don't know why. Maybe on the university's end, maybe they update WebEx in a way where you can't save it to your desktop anymore. So that way you're not able to use YouTube. Then maybe that's what they're trying to do. I don't know. But that was sort of an issue that they kind of did not want YouTube to be used for class WebEx recordings. So maybe I could do a setting for it, but I'm not really an expert on WebEx. I don't want to really be one because it seems like it's not really worth being an expert on this anyway. So, um, okay, so yeah, assignment 4 is due on Friday. So I will make I'll update this after class on Canvas so it still has the due date for tonight, but I'll make that change after class today. That's the only real update for right now. Our exam is in 2 weeks, so I guess I'll probably keep us more posted on that next week. So let's go ahead and I guess start a screen share and resume from last time. Zoom in on this because you really can't see too much here. So basically binary trees. I went over a pre and post order. So there's the code for that. So for your assignment 5, you're going to have to do some type of work involving pre and post order traversal, except you'll have to do more than just outputting the nodes, but this is sort of, the schematic or the apparatus or the method, I suppose, to process a binary tree. And so it's post order. So the same idea. So pre-order, you first process the node, and then you process the left and right subtree. For post order, you first process the left and right subtree, and then you process the node that you are currently pointing to. So just you swap the order of the recursive function calls, and in this case, the CL would be the quote-unquote processing of the node. In order is just another variation. You first process the left side, then you process the node that you are pointing to, and then you will process the right side. So that's, I guess you have a cout statement there, I suppose, if you want to output nodes in order traversal. And this is mostly only for binary trees, and mostly actually for certain type of binary trees is this in order traversal really even important. But I just thought I'd mention it now, but I'll mention it again later on. And then we have this function to find an element in a binary tree. So this is how it works. So r equals null. That means you didn't find the element. So if it equals null, that doesn't mean that it's not in the tree at all. It is that this path led to a failed search. Because unlike a linked list, for binary tree, you have a lot of different paths. Look at the following tree here. We have 10, 7, 3 is one path. Maybe you can't really see that, but we have 10, 7, and 3 as one possible path. We also have 10, 7, 11, 2 as another possible path. We also have 10, 8, 6, 1's path. We also have 10, 8, 6, 5 as a possible path. So if we hit null, that means that path we took led to a failed search. So we have to back up to the previous. You return false and you back up. Now let's say if you're pointing at a node and it equals s, you found the elements, return true. And this recursive function call here, well, if let's say either the left or right returns true, that means one of those two paths led to a successful search, so return true at that point is going to relay true all the way up to the very top. So when we go ahead and do a find 8, it goes ahead and looks at node 10, 7, 3, and returns false, then tries 11, 2, returns false up along this path, and eventually we call find on the right side, returns true, and then we went ahead and we found the elements. So I already went over this last time, so now I don't want to really go over it too much. I'll do one more example involving a binary tree sort of traversal slash work. Let's go over one where I want to count all the leaves in our binary tree. Let's go over that one next, then we'll sort of stop doing binary tree content, or at least this type of binary tree content. Let's go over code to count the leaves in the binary tree. So I'm gonna have a function, and this function returns a count, or the amount of leaves found on one side of our binary tree. So we'll say int count leaves. And once we pass in the pointer, bin tree node star r, which will just be a pointer that points to a node in our binary tree. And once again, we have to have our base cases outlined. So as always, well, we want to check for null. If we hit a null, that means we're done with that path. And also, we don't want to dereference a null pointer either, because that would cause a segmentation fault. So if r equals null, that means, well, this is empty. So it's not a leaf, it's just nothing. So return 0 in that situation. And then the following check. So we want to check and see if r is a leaf. Well, if r arrow left equals null, or null PTR, and r arrow right equals null pointer, and that means R has to be a leaf node, because a leaf means it's a node that has no children. So if R left is null and R right is null, it must be a leaf node. So we found a leaf. So return 1. We're going to count this leaf node. And then if you don't have these two base cases, that means R is not a leaf. So you want to go ahead and keep searching for leaves. So we're going to say return count leaves are left plus count leaves are right. Zoom out so we can see all of it. So basically all we're doing is, well, if you hit a null, then okay, fine, return 0 and we back up to the parent node. And if you found a leaf, well, return 1 to the parent node. And in the general case, what we always do is for any kind of binary tree type of work, it's going to be always the same sort of method. We do some work on the node that we're currently pointing to, but we also then we have to process the two subtrees, the left subtree and the right subtree of a node. So this is going to basically just count. Actually, I'll make this nicer. So let's see if I can see if this works actually. Oh, not quite. Let's try it again. But anyway, this side here is going to count all the leaves on the right side. Sorry, left side. My mistake. Your other left. I like this, but at the same time, it's sort of this work. Good. So this is going to count leaves on left. This is going to count the leaves on the right. And we add those up, that will give us all the leaves that are in the subtree of R, essentially. So, of course, recursion is all magic. I will do a quick trace of this. I don't want to really show, I don't want to do a long, boring half-hour example on this. I'll just do this very quickly of how this is going to actually work. I'm going to copy the binary tree used earlier because it's a good sort of example. So it's good enough. So let's go ahead and just use this one. Hope that I copied correctly. All right, looks like it works. So we gotta remove all of this out of the way, which is still much easier than drawing the entire tree. It's also, once again, very therapeutic to erase these for some reason. I don't know why. It's so calming for me. I don't know why it is. It just is. So anyway, the whole idea is really for binary trees in general, the same concept all the time. So any kind of problem involving binary trees, you have to always do the same type of work. You first process node R is pointing to, either at the beginning or at the end or in the middle, anywhere, anytime basically. And then we have to sort of do the same process on the left and right subtree. So we first go ahead and do this. What's going to happen is that when we start from the root 10, it's not a leaf or null. So you keep on recursively moving to the left until you finally hit this R, this node 3 is finally going to be reached. When that happens, 3 is definitely going to be a leaf, so return 1. Then for 7, we have to go ahead and call count leaves R right. 11 is not a leaf, and 2 is a leaf. So we return 1. And then we have to call 11's right side, which returns a 0 because it's a null pointer there. So at this level for 11, we have 1 on the left, 0 on the right, so we add those up and return 1. Then for 7, we called count leaves on the left side and the right side to return 1 and 1. We add those up, return 2. So for root level, the left side of the root has 2 leaves, which makes sense because those nodes 2 and 3 are both obviously going to be leaf nodes. And then for right side, we have to call count leaves on the root's right side. Go to 8, and then 8's left side returns a 0. So null pointer. Right side, 6 is not a leaf. 1 is a leaf. It returns 1. Then 6 will call count leaves right. Returns a 1 also. So we take the left and right side, which is 1 and 1, add those up, and return 2. Then for 8s, at that level 8, left side returns 0, right side returns 2. So 0 plus 2 is going to be 2. Then for root level, the left side returns 2, right side returns 2 as well. We add those up and return 4 back to main or back to wherever we initially call this function in our program. Basically how we do count leaves. So any kind of work on binary trees always follows this type of method. So of course you could also think about sort of function code as to how to count the number of parents that have only one child. So how do you write the code for that? Or write the code to compute the height of a binary tree, or write the code to output all the nodes that have 2 children. So on the exam, possibly could have something along those lines on the exam. Either you have to write out the code, or I'll give you some code, a recursive function call. I'm going to call it obviously foo or bar. I don't want to give it the name count leaves because there's 2 things that can go wrong with those. I guess I wrote here by accident. What could happen is 2 things. It will give you the answer almost in a way, or I can call it count leaves and have it do something entirely different, which will very much mislead you. So there's 2 things that can go wrong with this. So for that reason, I'm going to just call the functions foo or bar, and you have to sort of tell me what's this function actually doing. So for example, if let's say I gave you this function on the exam, if I called it in foo instead, just like that, I would ask you, okay, what action is this function performing? And the answer would be, oh, this function counts all the leaves in a binary tree. That would be full credit for that. If you write this on the exam, oh, if r equals null, return 0. If r left equals null and r equals return, if you start doing that, sort of like you write out the code in English for me, that means you probably might not really know what this actually does. You're just sort of just reading it off. It's like not really, doesn't convince me to really know what's going on. So for these kind of questions, less is more. So less words is better because if you write in too many words, that means you're probably trying to paraphrase the code and like write out what the code is in English instead of in C++, which is not convincing for me that you knew what's going on. I mean, I guess you're able to read the code, which is good, but that's not really enough. So you have to be able to give me like a better answer. What it's actually doing. If I gave you the code like on this function right here, let's say call it food, not find, same idea, you have to be able to make, oh, it's trying to find an element in a binary tree. Go ahead and say, oh, if r equals no, returns false. If n equals s, returns true. Otherwise, it's going to go ahead and call find left. Okay, that's not really convincing for me. So it's here on the recording. I'm saying it right now. So on the exam, don't be surprised if let's say you say that and lose points. Well, I said it here in class. It's on the recording. So it's on the record now, so you can't deny that I did not say this before. It's recorded, so that's kind of one of the benefits of having online class. You can't deny that I didn't know that. Well, why didn't you go to class that day? Well, I mean, you can watch recordings and you could have seen that. So anyway, um, so now I want to go over just a few sort of theoretical content involving binary trees. Let's go ahead and zoom in to our notes. So first of all, I'll draw like an actual I like to do like this instead. Yeah, or straighter, it still looks nicer. So so we want to go into what's the runtime. So for all these algorithms we covered right now. So preorder, post order, find, what's the one? Count leaves. What's the runtime for all of those? Let's first go over pre and post order. What's the runtime for this? Let's first look at the code and try to make sense of it. So let's go up to the very top. Let's go way back to our notes. Also benefit of using OneNote, so I don't have to actually, I can refer back to old notes. So here's our post order code. I can go to the pre-order code as well, but it doesn't really matter. The same sort of idea, same amount of work. So in our post order function call, there's no looping inside here. It's all just a bunch of C++ statements. So really, each node, the time it takes to process each node is going to be constant because look, every single function call, we're going to process a single node, which means this is all going to be constant work. But the issue is we have n amount of nodes in our binary tree. So we have n nodes. Each node we're going to do it a constant number of time, O of n. So let's put this here, the processing time for each node takes O of 1 time. And there are nodes in the binary tree. So therefore, the overall runtime, so total runtime is O of n. Not too complicated. So this also implies that not just pre and post order, but even that count leaves is also O of n. Even that find function is also O of n. So I'll put this over here as well. So for count leaves and find are also included because they really are based off of pre and post order traversals. So all these are O of n time, where n is going to be number of nodes in the binary tree. So basically, whether a tree is balanced or unbalanced, it's going to be O of n no matter what. So let's go ahead and first now go over balance of a binary tree, or what does it really mean, or what kind of heights can we expect to have for a binary tree? Because this portion right here is pretty important because we're going to go into structures and using binary trees to enhance runtime of certain algorithms, I suppose, or certain mechanisms. We want to use a binary tree to speed up certain things. So the height of the tree does sort of play a pretty big role. Let's go ahead and go over height of a binary tree. Sort of getting better at one node finally. After only a year and a half of using this, I'm actually starting to get the hang of this. So let's see. So we have we have two extreme cases. So I really want to show that because that's going to really be our best way to sort of encapsulate every possible scenario. So we have a binary tree like this. I'm going to put some zigzag here a little bit too. Just make it, yeah, I think I'll just stop right there. So we have this kind of binary tree, which is really just a glorified linked list. But this sort of binary tree can happen because every single node has at most 2 children, so this is technically a binary tree. So all linked lists are binary trees. However, not all binary trees are linked lists. So I guess that could be good to know for an exam. I'll say it again. So all linked lists are binary trees, but not all binary trees are linked lists. So anyway, this example, well, we want to go ahead and sort of count the heights of our tree. So we always start from 0. That's, I guess, a computer science thing. We always have 0 for our first height. So we want to get the number of levels of this binary tree. The level counter always starts from 0. It's a computer science thing. So this tree has a height of 5 because we have level 0, level 1, level 2, level 3, level 4, and level 5. So it's the height of 5 binary tree. And this obviously is a very bad case binary tree. I mean, there's no point even having a binary tree if it looks like this, but unfortunately, this can happen. So for this situation, well, the height h, well, let's say we have 6 nodes in this tree. Let me see, 1, 2, 3, 4, 5, 6. And the height will be sort of 6 minus 1. So n is your number of nodes, so height will be n minus 1 in this situation. So therefore, in this case, the height is going to be O of n. So for a very unbalanced tree, height will be O of n. I'll put this here. This is an unbalanced tree. In this case, or a very unbalanced tree in this case, but this is definitely unbalanced. So that's going to be so we want to know what's the possible heights of a binary tree. So anyway, now we also want to know, well, how many leaves do we have for an unbalanced tree? Let's go ahead and say amount of leaves. That's going to equal 1 actually, because you have to have at least one node where the paths will finally stop traversing. So for a very unbalanced tree, you will have only one leaf, or I guess this will be sort of like, not really a lower bound, but this is sort of, you have to at least have one leaf. It's not a real lower bound per se, but it's sort of a minimum requirement. You have to have at least one leaf for a binary tree. So here's a very unbalanced case. Let's go over a more balanced binary tree and sort of go over its height. So let's go ahead and draw this up. So we have a more balanced binary tree. in this example. I'm going to create several levels. See if I can create another level. If I can't, well, I'll be able to. It'll just look kind of awkward. I don't know why each circle is different size in each level. That's 100% arbitrary. I guess I was trying to fit nodes in each level on the frame on the screen here. So it's supposed to be all the same size circles. That happened. So here's a very balanced binary tree. We'll go over later on as to really have a more formal definition of what it really means to be balanced. But for now, we'll just go ahead and say that, well, this is definitely a pretty balanced binary tree. It's actually fully balanced. It's perfectly balanced. So once again, maybe I'll move this over here. Hold on, this is kind of going to block the way. So put this, sorry about that. Otherwise it blocks notes over here. So once again, we want to get the height of this tree. So the very first level will be always level 0, level 1. So we have, this is level 0, that's level 1. This will be level 2, and this will be level 3. So this is a binary tree of height 3. So you have to sort of take the biggest level index, and that's going to be the height of the entire tree. If it's a little bit unbalanced, let's say one side is bigger than the other side, well then the max height. So for example, I'll just put this here really quick. So let's look at this tree, for example. Height of this tree would be 0, 1, 2. So it's whichever subtree has the biggest height, that's going to be the height of the entire tree. In this case, it's fully balanced. If you have it like this, the bigger subtree height will be the height of the entire tree. So we'll do examples of that, of course, later on as well, but just to let you know. Okay, so this will be a balanced binary tree of height 3. We always start our counter from 0. That's just sort of how it works in computer science. Also in Europe as well, you don't have the first floor. The ground floor is always floor 0, and then floor 1 is the second floor. So I guess sort of Europeans might, maybe they're thinking binary tree as well, or I don't know. Europeans have all kinds of ways of doing stuff, so it can get. I mean, I was in Europe many years ago, so it can be a little bit. Sometimes they have all these rules as to why. This is just why. Anyway, not important. So let's go ahead and now go over. Well, what's the amount? You want to go ahead and figure out the height of this tree. So in the above example, first have to figure out how many nodes our tree will have, and then compute the height from that. So it's very simple. This is just, well, we have n nodes, n minus 1 is our height. We want to figure out what is going to be n in this case. We first have to figure out, well, what's going to be, we have to count all the nodes in this binary tree. So in our first level, we have actually 1 node. Next level, we have 2 nodes, then we have 4, then we have 8. That's a pretty nice pattern we're seeing here. So we actually can write this in the following way. So we have 2 up to the 0 number of nodes in that first level, 2 up to the power 1, then 2 squared, and then 2 to the power 3. So that's going to be sort of how we can compute these. So this will give us 1, this will give us 2, 4, and 8. So really it's just 2 to the power whatever level we're currently on. It's going to give us how many nodes at that level if it is nicely balanced like this. Okay, so we want to go ahead and sum all these up and then figure out what's the height of this. So this is sort of a specific example right here, but we actually can formalize this summation using the following, following formula. Another summation, yay. So this is going to give us n, the number of nodes, because we're adding up. So adding up 2 to the power 0, plus 2 to the power 1, plus 2 to the power 2, and so forth. So this summation has a very nice closed formula for it. So if we go ahead and add up, so 2 to the power I from 0 to 8, this is going to give us the following result. We're going to get 2 up to the 8 plus 1 minus 1 equals n. So basically, it's just this summation. Try to use that box so it's a little better. Try to do that. It's really just going to be, we're going to replace it with this because this formula models that one perfectly. Let's get the straighter box here. Perfect. So that's all we did, really. We just sort of use this formula. This formula does perfectly work. Let's go ahead and sort of do one example right here. So in this example, 1 plus 2 plus 4 plus 8 is going to give us a total of 15. Okay, so in this binary tree, the highest will be 3. So 2 to the power 3 plus 1. So 2 to the power 4 is 16. Minus 1 is 15. So therefore it works because for one example it worked, therefore it has to work for all examples. Actually, you can prove it using induction, and the proof actually is sort of almost like that. It works for some arbitrary example, and it works for the next example after it, therefore it works for all possible examples. So with induction, you can very easily prove that this is going to work. So induction proofs are just like recursion. They're all magic in terms of how it works. It's magic, the proofs. You basically just assume it works for certain cases. It works for that one case, and it works for the next case as well. It works for all cases, which is, I don't know, for me at least, induction is always sort of magic how it works. But anyway, so we have this formula, and we know what n is. You want to solve this for h. You want to know what is h going to be in this particular case. Well, let's do a little bit of algebra here. So I'm going to say 2 to the power h plus 1 equals n plus 1. And now we can go ahead and apply this function, which is I'm going to go ahead and take the log of both sides, log base 2 of both sides. So log 2 of 2 to the power h plus 1, it brings the exponent down. It'll be just h plus 1 equals log 2 n plus 1. I took the log of both sides, basically. I'll put this here for a second. So take the log 2 of both sides. That's all we did. And log 2 of 2 up to the power whatever, we bring that whatever down, h plus 1. And we solve for h, a simple algebra problem. H equals log 2 n plus 1 minus 1. And using L'Hopital's rule, we can very easily show that this is going to be the same growth rate as log of n. So h is going to be O of log n, where once again, n is going to be the number of nodes in our binary tree. So we have these two different bounds. We have O of n and we have O of log n. Now also I'll do one, actually I'll talk one more time, I'll say one more thing about this. So we also want to go over the amount of leaves we can have. So here we have 8 leaves, which is really just 2 to the power whatever h is. In this case, h is 3 in this example. So for a balanced tree, the amount of leaves is 2 to the power h. It's actually kind of interesting that the amount of leaves and the amount of total nodes in our tree are actually going to be relatively asymptotically the same. I might have given away a part of an answer on homework 3. So 2 to the power h or 2 to the power h plus 1 asymptotically are the same. So it's kind of nifty that for a binary tree, the amount of leaves, if it's fully balanced, the amount of leaves and amount of total nodes are about the same. So, of course, if you're given a perfectly balanced tree of n nodes, then the highest will be always just log of n. We also can kind of guesstimate this and say, well, if it's a perfectly balanced tree, if I take log of the number of leaves, that'll also give me the highest. So you can take the log of the leaves actually as a shortcut. Sometimes it can be beneficial. So the log of the leaves is going to be the same as taking the log of all the nodes in our tree. It'll be the same value or similar value, maybe off by 1 or something, but not a big deal. So It's kind of nifty. The number of leaves, number of total nodes for a binary tree is asymptotically the same if they are balanced. Okay, so those are our two heights, log of n and O of n. So what's the height of a binary tree then? Well, we have to consider the worst case. So the worst case is O of n. In the best case, the height is O of log n. Those are our two results. So worst case height, O of m, best case height, O of log n. Case is this. This will be our worst case. Actually, I'll box this in as well. So just to be consistent. This will be our worst case. We have these two different bounds, two different heights, basically. And this plays a pretty big role when we go over other algorithms involving binary trees. But for now, we have the whole binary tree content down. We sort of know how to traverse binary trees, and we can sort of, now we know that there's two possible heights. Either it's log of n, or worst case, O of n. Those are two extreme cases. So our goal is we really like to have the height to be O of log n. If it's not O of log n, the height, that means really there's no point even using a binary tree because, well, we're just doing work essentially on a linked list, which we already know how to do, right? Because for CS 202 and for my first assignment in this class, we're now experts and we're experts and we sort of embrace linked lists, but we also at the same time we very much don't like linked lists, so we want to avoid linked lists. So log n height means we're doing an actual binary tree. We're not actually sort of doing work on a linked list. So anyway, let's now go over our next sort of concept. So it kind of builds off of these height concepts. Let's go over binary search trees. These are binary search trees. So basically a binary search tree, well, it's a search structure. So I'll put that here. Say search structure. So what is a search structure? Well, it's a structure for searching. That's a very bad definition, but really that's kind of what it is. So essentially, it's a structure that's designed to quickly search for something is the idea. So think of the following example. So you come home from school and you drop all your papers and all your contents somewhere on the floor or somewhere without organizing it. That sort of was a very quick operation. I was O of one time to do that. You just sort of drop your stuff somewhere, O of one, constant. Perfect. Now let's say every day you keep doing this. Each day it's constant time to sort of drop your stuff, all your papers, and they sort of pile up at some point. Let's say you have like, your letters, your mail. Okay, that's probably better. You have your mail. Every day you get your mail, and you sort of just put it somewhere really quickly. Let's see, what does Yes, you could say that. If you ask, what does the binary search tree do? What does it do? It just searches for something. Yeah, that's sort of the idea. So that would actually work. But luckily, that question won't come up probably because that's a very ambiguous question because, it's too philosophical to have on an exam. So that's sort of why we can't have that on an exam. So let me see. So let's say we have our letters and we just sort of drop them into a pile. That's all of one time. We get letters next day in the mail. We drop into a pile all of one time. But then if you want to go ahead and find a specific letter, well, you're going to have to kind of shuffle through your letters and find it. So that takes O of n time to do that. So an array can be a search structure or a linked list. We just sort of insert to the back of the list every time we get new elements. When I find something, it's O of n time to find it. So it's very quick to insert, but then you pay a price when trying to look for something. A search structure is going to be the following. Have a bigger setup time where imagine you have your letters and you, instead of just sort of throw them somewhere, you try to, arrange them in a certain way, either by date or alphabetically, whatever. That time could take a little longer. Well, I guess in this case it wouldn't, but guess you want to sort of sort them by importance, by type, by whatever you want to sort them by. There we go. That's a good example. That might take some more time to do. But then when you want to find a specific letter, it will be very quick as well. The search structure is designed for fast searching, but the bottleneck is, or the problem is, you have to spend more time inserting elements into the structure, where there's more overhead to insert, but then you save by looking for something. So that's sort of the whole idea of a search structure. So we're going to cover really two real basic search structures. One will be binary search tree. The other one's going to be a hash map, which is a very fast search structure, but it has also a price it has to pay to make it very quick. So anyway, let's go over the first one, binary search trees. So basically, all it is just a binary tree arranged in following way. So then each node. So actually, my mistake. I should probably move this. I'm going to go ahead and sort of move this down for 1 second. All right, one more piece of node here at the right. So let's do one little quick thing. So every search structure contains a key value pair. So typically, you search for some key value, some key element, and then you want to retrieve the value associated to that key. Now, for binary search examples, or binary search tree examples, sorry, we're going to actually make it where the key and the value will be the same entity. So, because I guess there's no point in separating them now, because conceptually speaking, it doesn't make any difference. So we'll make it where the key and value will be the same. But in theory, or not in theory, but in reality, every node would have sort of two contents, a key, a search key, and a value associated with that search key. So in a binary, a binary search with a binary tree, sorry, it's supposed to be, I don't know why I wrote it off in a bad way again. Just go ahead and fix this. Binary tree. Tree. Arranged in the following way. So for each node, its key, search key, will be larger than its left child's search key and smaller than its right child's search key. In other words, right child will have a bigger key value and the left child will have a smaller key value. And we can also sort of expand on this. So for each node, the left subtree, so the entire left subtree, all contain keys that are smaller. The right subtree, entire right subtree, contain keys that are larger. So having this binary tree in this sort of form is going to allow us to be able to search for elements quickly. That's the whole concept because, well, it depends on the height of the tree, but this is basically what we want to do. We want to ensure that this is going to be maintained in this binary tree, this property, essentially. Now, you may wonder, what about for duplicate keys in your structure? What if you have matching keys? Well, for any search structure, you don't want to have duplicate keys. If you do, it's going to cause a problem because a search structure you want to find, let's say, for example, you want to find John Smith. If you have exactly two John Smiths in your structure, well, then the question is, well, which one do you want to look for? So you have to somehow be able to distinguish every node, or else you can't really tell which one you're trying to find. So it'll find one of them, but maybe it'll be the wrong one. Who knows? So each node has to be distinguishable somehow, or else it's sort of wrong. It's imagine we want to search for a person based on phone number, and we have two separate nodes, the same phone number. Well, then which one do we retrieve? I mean, okay, I'll pick one of them, but I mean, maybe it's not the right one. Who knows? So make sure you want to have always every key value has to be different in a binary search tree, or any kind of search structure for that matter. So now we're going to just go over some example binary search trees, and of course, write some code to traverse and do work on a binary search tree. Let's go ahead and do that next. So we're going to have a binary search tree. I'll just create one, just a simple one. Yeah, good enough. So it's just a binary tree, but we have to make sure that the elements are arranged in a certain way. I'll have my root over here as always, just have my root. I'll have, let's say, 15. I'll say 7, and 3, and 2, 20, and 25. So the numbers inside these nodes will be our keys, but we'll have it where we're not going to really focus on what the actual value is. So we can almost consider it where this will be a special kind of binary search tree where the key and the value will be the same element, same thing. So we're going to focus mostly on the keys, or search keys, not really on what's actually stored in the value field of each node. But notice this will be a binary search tree because for every single node in our tree, the right child contains a bigger key value and a left child contains a smaller key value. Now, if you have a leaf that has no children, well then it can violate the binary search tree property. So very simple property to maintain. So there we go. So let's go over, well, how do we actually find something in a binary search tree? Okay, let's go ahead and write that code, and we can kind of see how a binary search tree is more of a better structure than just an ordinary binary tree. Let's go over how to do a search operation. So bool, I'll call it find. And then we're going to pass in our bin tree node pointer. I guess I won't template this, so it'll be just a regular, so it'll be integers for our keys, I guess. So we'll just do it like that. So once again, we have our base cases. If r equals null, turn false. And difference here is if a false is returned, that means S cannot exist in our binary tree. Because since we arrange them in a certain way, there's only one possible path, only one location where S could possibly be. We'll show you in a second why that's the case, but Either way, return a false on null. And then I'll just say if R arrow, I guess I'll say key for right now. Could be R arrow item if you want it to. It doesn't really matter. We're not going to focus too much on, I'm not going to distinguish between the value and a key, but some type of, well, I guess in this case, I'll use key right now. But if you use R arrow item, it'd be just as good because we can sort of think of it as the key and the value will be the same thing. But either way, though, if you find a match, then return true. And here's where it's a little different from a regular binary tree. The following will do. So we'll check. So if R arrow key is less than its S value, if that's the case, that means if S does exist in this binary search tree, it must appear on R's left side. Somewhere on the left it has to appear. So we're going to return find R arrow left and pass in that search value. And then I'll have an else case. I don't have to have else if, because if it's not less, if S is not larger, sorry, my mistake. Oops, if S is bigger, my mistake. Supposed to be on the right side. I apologize. My mistake. So let me re-explain this. So if the S value is bigger than a key, S has to appear on the right side somewhere. It's my mistake. I'll say it again. So if S is larger than that node's key value, then S must appear on the right side of our binary search tree. And else return find R left. And we don't have to use else if, because if S is not bigger than a key, then S must be smaller because we check if it's equal above right here. So of course you could say, well, else if, but we don't have to because we know that if else case happens, S has to be less than the key. So S is less than R key. That means if S does exist in our binary search tree structure, it has to appear somewhere on the left side of our tree. So notice, I guess I have my other notes, another sort of page, but good enough. So in this situation right here, we see that we don't try every possible path in our binary tree, only try one path. So the idea here is that in the example from before, we would go ahead and do a find on the left side. If it returns a false, then we would try the right side. But here we're not going to do that. We're only going to pick one side and that's it. Because S can only be in one location in our binary search tree. Let's go ahead and just explain why. So looking up over here, let's suppose I want to go ahead and call find. I pass in root. I pass in 10, my S value. So I'm doing this, I first start at this level. I start over here first. I check, it's not null, and it's not a match. Okay, well, I'm looking for 10. So since we have our binary search tree order maintained, if 10 does exist in this binary search tree, well, it cannot appear on 15's right subtree. It can't be there because 10 is smaller. So we automatically can eliminate these nodes from our search. There's no point even to look over there. For regular binary tree, well, we can't assume that it could be there somewhere, but for binary search tree, we know for sure there's no way 10 can possibly be there. So, okay, fine. So if 10 does exist, it has to be somewhere on 15's left side. Let's go ahead and call find again and jump to the left side in the situation. Okay, so now we're looking at this node 7. Yes, so for binary tree, the entire left subtree will contain all nodes that are less than the parent. So 15, even though 10 is bigger than 7, but 10 is less than 15. So everything to the left of 15 are all going to be smaller than 15. And likewise, all the nodes to the left of 7 will be smaller than 7. Everything to the right of 7 is going to be larger. So 16 could be in this tree, but it would have to be on 15's right side. Now right here we don't see one, so we'll do an example. If we're trying to find 16, what's going to happen? But anyway, let's go ahead and continue on this example. So I jump to the left side of 15, and I check. Well, it's not null, and the value is not equal to 10, so 10 is bigger than 7. So if 10 is in the structure, it has to be somewhere on the right side of 7 if 10 exists. It cannot be on the left side, so because 10 is larger, so 10 cannot be over here. So these nodes, and from earlier, these nodes were automatically, without even looking at them, we eliminated them right away because we know that 10 cannot appear on the right side of 15 and it cannot appear on the left side of 7. We know that. There's no way because if we assume binary search tree order, it has to be on 7's right side. Let's jump to the right of 7. We got this node 10, and it's not null, but now the key value 10 does equal to s value 10. So we found 10 in our binary search tree. So return true. Every level above, if you notice, we simply return what the child returns. So we kind of just relay that true or false value all the way up to the root. We just relay it basically. We simply just return what the child returned. So in this situation, 7 is the parent of 10. 10 returned true, so a parent returns also true. Just relays that true all the way up. So we found 10 in this binary search tree. All right, let's go ahead now and do another example. We want to go ahead and find a different node. Let me go ahead and recopy this tree so I can actually do another example of this. Sort of make the notes a bit nicer when I post them on Canvas, but this will be good enough for right now. So let's say I want to do a find. I'll say root 24. I can also do 16, same idea. Well, okay, I'll do 16. 16. So in a situation, well, we start from the root as always. Jump over here. And we check. It's not null. And well, the key value there is not 16. And since 16 is bigger than 15, that means if 16, if it does exist in the structure, it must appear on the right side of 15. So it has to be somewhere here. So these nodes right here are automatically eliminated from our search because we don't have to even look. We know that 16 cannot possibly be there. If it was there, then this is not a binary search tree. We have a regular, ordinary binary tree. If it's a binary search tree, we know the order is maintained, so 16 has to be on the right side somewhere. So those nodes are automatically eliminated from our search. To jump to the right side, check this node. It's not null, and it's 20, which is not 16. So that implies that if 16 does appear in the structure, if it's in the structure, 16 has to appear on 20's left side. So that means the right side of 20, these nodes, or in this case, this node, is eliminated from our search because 16 cannot possibly be on 20's right side. So these key values are like a guide that kind of help us determine which side to choose. In a regular binary tree, we have to, so for binary search tree, when we hit a node, based on that key value, it'll tell us to go left or right, based on what the key value is. For binary tree, when we hit a node, okay, which side do we take? And the answer is yes. It means we take both sides because we don't know. We have to try both because we can't assume that's on the left or the right. But here we can make the assumption. So we can't just say yes, we have to, traverse left or right, pick the left or right path. So here I pick the left path because 16 is on the left side of 20 if it exists. And left side of 20, well, it's a null. Because left side of 20 is, there's no child there, we hit a null, which means, well, that means we did not find the element. So for regular binary tree, you could say, well, it returns null, let's try the other side. Well, here we don't have to because there's no point. The 16 cannot appear on 20's right side. So returning false automatically. And simply, you can notice over here, we simply return what the child returned. We just simply relay up the tree. So return false here, return false over here, and then return false. That's basically the idea. We sort of follow these key values, give us a guide as to which path to take. At some point, we'll find that node sooner or later. Once we do, return true and relay true all the way up our tree. If we hit a null at some point, that means we didn't find it. And it doesn't mean that, oh, that path up to a false. That means it's not in our tree at all, because we know that there's no point trying the other path because we know it can't be there. So that's sort of how this find operation works. So then, okay, so for this find operation, what's the runtime of this? And the runtime for this, well, it's the height of the tree. So the runtime for find is, well, it's going to be depends on the height of the tree. Which means that in the worst case, it's O of n. Best case, O of log n. Depends. If the height is log of n, this will take no more than log n number of steps, because in the worst case, the element happens to be a leaf. So trying to find an element or find a key value, and the node we're looking for happens to be a leaf node in the worst case. So every search, worst case, the leaf node is what we're looking for, which means you have to run this find exactly the height of the tree number of times. So if it's a very bad binary tree, it'll take O of n time, O of n steps in the worst case to find its element. If it's a balanced binary tree, then it will take at most log n number of steps. Never more than log n, because it's going to, once it hits a leaf, we're done. Or let's say, for example, we're searching for an element that's not in our binary tree. Even then, it will take at most height number of steps for us to know that this element we're looking for is not in our tree. So the idea is that it depends on the height, really. And the height can be O of n or O of log n. So if it's a balanced tree, it will take no more than log n steps to either find element or to determine that the element is not in our tree. If it's a very bad case binary tree, it will take at most n steps to determine, to find the element or to determine if the element does not exist in our tree. So a question here, how long will it take to create a binary tree? That's a good question. And I guess we will have an answer for that, not just yet, but we will go over now how to insert into a binary tree, and then we'll have a good idea of what's the runtime it takes to build an entire binary tree. So we're getting there is the answer for right now, but we'll have an answer shortly. Either by the end of today or definitely early next time, we'll have the answer for that. So let's go ahead now and go over insertion into a binary tree. Yeah, go ahead and I'll copy this tree in case I use it right now. I'm going to copy this. I'll use this example for inserting. So inserting. Now, There's a simple syntax for it and also a hard syntax for it. The more complicated syntax is used because this method allows us to modify how insertions are done. We'll go over what does it mean to modify, but we want to make sure that we want to take this insertion code and be able to modify it slightly in certain situations. That's definitely going to be for next time's lecture, but let's go ahead and just talk about this insertion right now. It's a very weird sort of code, very weird prototype for this function. Bin tree node star insert bin tree node star r. And I'll have maybe int k for the key, I guess. So this function returns a pointer that points to a binary tree node. Yeah, I'm going to do some tracing on this code very slowly so we can see what's going on here. And I'm not going to really show the code for this other part, but the idea is I'll paraphrase it later on. But it's very important that we return a pointer instead. It makes it very easy to modify this code to be able to handle. So essentially, it's because if you want to balance the binary tree, having returning a pointer is going to make the whole balancing process very easy. That's why. So if you need to balance a tree at some point, returning a pointer will make that balancing a very quick process. Let's go ahead and go over this. So insertion. So you first have a case if r equals null. If that happens, this really implies that we found a vacant spot for k to go into this binary tree. So this implies we found a vacant spot. And I'll put a comment here. Found a vacant spot. So we found a location of where k needs to go in our currently existing binary search tree, sorry. In this situation, I'm going to create a temporary node pointer, so node star, bin tree node star, my mistake. Better. Bin tree star, I'll call this temp, equals new bin tree node. So if r equals null, we're going to actually insert a node into that null location. So then temp key, or whatever that is, a search key, we'll set it equal to k. And a value, we could set some default value to it, but we'll focus just on that key field. So we're going to focus only on that for right now. And then this will be, in fact, a leaf node. So we're going to set the left and the right to both be null. And then we're going to return temp. So the idea here is that we create this new node, return it, and a parent above it will catch that temp and assign that to the left or right side of that parent node. So parent node, either the left or right pointer was a null. Returning temp is going to fill in that void or that vacant spot of that parent node. We'll do an example shows you how this actually works. Now, if r is not equal to null, we have to go ahead and sort of find the location of where this key has to go. So for insertion, we essentially have to do a search. We gotta find where would key ought to go. Once we find where it ought to go, we're going to create the node right there. That's the idea for this. Let's go ahead and just write the remaining code for this. So if R, P is less than K. If that's the case, that means this K value ought to go to the right side of R. It has to be somewhere on the right subtree of R, maybe a direct right side, or it's going to be somewhere on the right side. So what's going to happen, we're going to say R arrow right equals insert R arrow right. Okay. So this insert function always returns a pointer. So R right is going to be a parent. So we're passing R right into the function. It returns a pointer and a parent. So in this case, this is going to be the parent node. Will catch the result of what the child returns. We'll definitely trace this out in more detail, but that's sort of the idea. Of course, else case. So if the key is not larger, the key must be smaller because we don't want to have duplicates in our binary search tree. If we have find duplicate, let's say, for example, if our key equals K, then return. By the way, stop. Don't insert this because we don't want to have duplicates. But we're going to assume for right now that we're not going to insert duplicates. But of course, you can have a case that checks for, let's say if our key equals K, return. Don't do any more work. Don't insert anything. Just get out of this function because we don't want to insert a duplicate, but we're not going to worry about that right now. So if the key is not larger, key must be smaller, then that means the K value ought to be somewhere on the left side of R. This will insert K somewhere to the left of our pointer R. And then at the end, very end, so this is not part of the if or else, is a separate statement outside of this if else, return R, which returns the pointer back to the parent. Very bizarre, but the idea is really this. I'll zoom out so we can see the entire code in one frame. Yeah. So basically all we're doing is the following. We're searching our binary search tree, trying to find where would K have to go in our current tree. So it's sort of like if I had a key K in my tree, where would I go? We had to find that that element in our, or that spot in our tree where K would have to go. Once you find it, we insert K into that spot. So let's go ahead and do kind of a very high level view of this. Now we'll go ahead and do more the details later on. Let's go over this very quick example as to how this actually works. So we'll do the more step-by-step as to how this code actually will do this. So for example, I want to insert 16. So I want to go ahead and say root equals insert 16. What happens is we'll have a pointer pointing here. 16 must be on the right side, pointer here. And then we see that the left side of 20 is null. It's a null pointer right there. So if 16 does exist in our structure, it has to appear on 20's left side. So we're going to go ahead and just create this node right here. That's what we're doing essentially. We have to find where would 16 have to go. So 16 is bigger than 15, less than 20, but 20 has no child, so that's where 16 has to go. We find our first vacant spot in our tree, and since it's a blank, that means 16 is not in our tree. That's where it would have to actually go. We insert it right there, and that's it. So that's sort of how insertion works, but we'll go over how this code actually does this, but we're essentially doing that. If I want to insert, let's say, 9, let's say, for example, just very quickly over here. Then we'll do a more in-depth example next time, but I'll just very quickly insert 9. So 9 is less than 15, larger than 7, less than 10, and 10 has a null, so we're going to insert 9 right there. So 9 has to go there because so less than 15, greater than 7, less than 10, so 9 has to go there. Insert 9 right in that spot. That's sort of how this works. So I guess that's it for right now. I'll do more examples next time with this, but for right now, take care, you guys. Thanks for watching. Stay safe, and I will see you guys next time.